Hi, Maya. Thanks for sending those slides. All of the slides that you sent me are all formulas using the sigma or the summation notation, and I think that may be what's putting you off a little bit on these. So I thought I'd just give you a general explanation first of all, and then we'll talk about the individual ones, okay? So this Greek symbol is sigma. It's kind of like a backwards 3, but it's got those sharp angles on it. There's another sigma that we use in like data management and statistics, and it looks like that. And that's just the lowercase sigma in the Greek alphabet. We're not going to use that in this course, I wouldn't think, but just in case you see it, okay? All right, so the summation notation, let's just pick a really easy one. Let's just say it was xi, and then we're going to have I equals 1 to 20 or something like that. And that was kind of dumb of me to put in 20. Let's do something smaller because I don't want to write 20 numbers out here. Let's do 5. How about 5? Oh, it just doesn't want to write up there. I see. Okay, let me pull that down. Okay, so all that's telling you is that it wants you to take the first 5 terms and just add them up. It's really shorthand. It's just math shorthand, and so they don't have to write a whole bunch of instructions and words. And so let's say I have a group of numbers that are my x values. And so x1, the first x value, is equal to 2. x2, the second x value, is equal to 5. And we're just going to keep going up in order here. So I'm going to have 11, and then my fifth x value would be 14. So what this summation notation would mean is this is my I, it's the ith term, and that sounds weird. It means first term, second term, third term, and so that's just the general notation for any term in our group of numbers that we're working with. And the 5 at the top tells me how many terms total I want to include in my sum. And this xi with the summation beside it is saying add up all of these terms. Okay, so all I need to do then is just get my calculator out and add these guys up real quick, and I think we're going to get 40 maybe, I don't know, 10, 21, 26, yeah, 40. Okay, and so in this case, the sum would be equal to 40. And that's all that means. And so I just wanted to show you that with a much easier example. And of course, whenever you come across letters and stuff, having real numbers to put in makes it so much easier to understand. So if you can fast forward through lecture notes or text or whatever you're using and find one where they've actually worked it out with numbers, it's going to make it a lot easier to go back and look at it when it's just with variables, okay? All right, so for this guy, we've got G, and G is defined according to this equation. So it means that we're going to take the sum, and we're going to start with the first term, and K is just general. It's just like for any amount of terms, so we have to fill that in later if we want to get an actual answer. And what we're going to do is we're going to take the pi squared, and so that's each p value between 1 and whatever k is, and we're going to add all those together. And so this is a frequency, I guess, that what that p stands for. We're going to take those frequencies, we're going to square them, and then we're going to add them all up, okay? So if you had a bunch of frequencies given to you, like maybe 1, 2, 3, I have no idea what the actual numbers are, if they're whole numbers or not, because I don't know your course, but the first thing I'm going to do, if these are my p-values, is I'm going to square them. So 1 squared is 1, 2 squared is 4, 3 squared is 9. And then I'm going to add them up. 1 plus 4 plus 9, and that's just 14. And that's it. That's what that means. And so down at the bottom here, it says the locus heterozygosity is simply 1 minus g. So once you've done that summation, that's the hardest part. So then you're going to take h, and you're going to say that it's 1 minus 14, and that would give me negative 13, and that probably makes no sense whatsoever in terms of your course, but it's the math, right? It's just, it doesn't really matter what the numbers are right now as long as we understand how to use them in this formula. Okay, so I did a little bit of looking into this one and figured out what this formula is actually asking you to do. An easier way to write this formula and to understand what you're supposed to do with it is for you to write it like this. So what they're actually asking you to do here is for each of the frequencies that you want to find, A1, A2, A3. Let's do PA1. Okay. What you do is the first one is going to be your A1. That's what that means. And so A1 is 0.2. So we're going to put that in our formula. And then we're going to take a half or 0.5 times the combination of A1 with one of the other alleles. And so A1, A2 is a combination of A1 with A2, and so we're going to take that and put it there. And then the next part of the formula is asking us to take a half of the combination of A1 with A3, which we are also given right here, 0.30. Okay. So if I add all of these up, I'm going to get 0.45, and that is the frequency of A1. Okay. So if we keep going with that idea, then we can calculate separately the frequency of A2. So we're going to start off with A2, which is 0.16. And then we're going to take a half of the combinations of A2 with the other alleles. So A2 with A3 was given here, 0.14. And A2 with A1 was given here, it's 0.2. And so if I add those up, I'm going to get, I think, 0.33. Okay. And so you'll notice that if we tried to calculate the frequency of A3, we don't have enough information because the first thing we would do is start with A3 as our first term, and they didn't give us that. But the reason they didn't is that all of the total of the frequencies have to always add up to 1. And so I've already got 0.45 and 0.33, so if I'm going to do the frequency for the third allele, then I'm going to do 1, take away the frequency for the first one, take away the frequency for the second one, and whatever's left over there has to be the frequency of the third one. And so that's what that scary formula is telling you to do. So I would rewrite it as, maybe as an example of what it's asking you to do, like A1 plus 1 half times A1, A2 plus 1 half of A1, A3. That's what that crazy formula means. Okay, for this last one, it appears that I looked up an example of this one so I could explain what it means here. So all that you're doing here is if you have a number of different combinations of the genotypes, so let's say we have the genotype AB, and so these can be combined in any way, like a Punnett square kind of thing. So we can get AA, AB, another AB here, and then a BB. And those would be all of the possible outcomes if we are mixing and matching these. And so if we were looking for the observed heterozygosity, then we would be counting the number of each type of combination. So let's say that we are trying to find the observed zygosity of AB. Then we would count the number of times that AB appears in our chart, which is 2, and we would divide that by the number of total combinations, which is 4, and so that would give us a 50% or 0.5 heterozygosity. I've learned a new word today. So that's all this formula is telling you to do, is just count up how many of each type, and then if we're looking specifically at just one of those, we put that on the top and we divide by the total on the bottom.